Okay. Right.
Yes,
All
we
right,
see the
guys.
slide right now.
Apologies for the delay. As usual, technical logistical issues. Welcome to the class on deep learning. This is lecture 3. Let me close the door, I guess. No, probably doesn't matter. Hey, if you're new to this, my name is Mithun. I'm a research scientist here at the Data Science Institute. We are in an introduction to deep learning class. So this happens every Thursdays, 1 p.m. At the Weaver Science Engineering Library, room 212, or on the Zoom link that you are on right now. So in the last class, we saw introduction to transformers. So in this class, let's see. So in the last class, we had seen all this, right? The typical types of training transformers that happen. And today we are going to get a little bit deeper into transformers. Like earlier, we had seen pre-training. So the whole idea of transformers, or the fundamental building block of any AI network right now, is that first, it is trained on a ton of data. And the ton of data could be the whole internet, or there's a huge corpus that you're trying to learn from. So you're not training for a particular task. You are just throwing everything under the sun to a transformer model. And the way people do these days after that is, say you want a question answering chatbot. So then the first part of training it on everything under the sun, which is to make it understand the connections of words and semantics, that is what we do by pre-training. So once we do pre-training, we want it to say, for example, a chatbot very specifically for your medical data set. Then we do something known as fine-tuning, which is retrain the whole thing again, but in a very small data set environment. So right now, we are working on fine-tuning a transformer model, or like eventually we will learn how to fine-tune GPT probably in the next class. And the idea is that we don't want to run pre-training or the original training. The original training will take hours and hours, if not days, and huge amount of computing resources. So which is why open source GitHub repositories like Hugging Face has already provided you with pre-trained models. So what we will be learning right now is fine-tuning one of those existing pre-trained models. So just to remind you, the way we were, so this was another way we can do transfer learning. We saw that people don't really use this anymore after the big foundational models like transformers came up. Transfer learning earlier was, let's train our model to identify cats and dogs. Now let's ask it if it can identify car and truck. So that was known as transfer learning. And then we saw that this is what I was telling you about. Like earlier, we were talking about in the last class, we take a large model and keep training it on multiple days, huge corpora, etc. And now we are going to fine tune it. We saw this earlier. The way transformers work is you take text, raw text, convert it into tokenizers. We throw it into a model who gives us predictions, what we call logits, and then we do some post-processing on it to predict A or B. So remember, this was only one of the very few tasks where we are asking it to predict between two classes. For example, the sentiment of a given movie review. But of course, that is only one of the very basic things. There is definitely tons of other tasks like chatbots and QA, which we will get to. And in fact, my goal in this class is to train you to be able to create your own chatbot like GPT for your favorite data set. So you can bring in any data you want, fine-tune your model on that, and now you can ask questions like, let's say you have a bunch of news articles particularly for one single football game that happened yesterday. Remember, models like GPT was trained 6 months ago. I don't know if they're continuously training still, but they definitely don't have data from yesterday's football game. So we will be able to train GPT on yesterday's football game text and start asking it questions. So that's an ideal scenario. Let's see how we get there together. Yeah, we saw this just now. And we saw all this last time that we throw the model a bunch of data, it goes through layers of neurons, and the model output. So just refreshing from last class. Okay, so this one is, I think we saw this last class, unless you moved it. All right, cool. Okay, so this class I'm intending to be lots more hands-on and lots more interactive than more theory. We will talk about theory as and when we get there. So this is what we saw last time. Was, if you don't know how to get there, just go to the UA-DataLabs data labs. So that is github.com UA-DataLab DL workshops. And here we have workshop 3, fine-tuning a pre-trained model. These things are still outside. I'm going to move it there, but click on without batch. So this is what we saw last time, which I just opened here in Colab. So remember, Colab, the only problem with this is every time you start a new session, you have to start installing from scratch. So we have to again do pip install transformers. And what we had seen last time was we can take an existing model, fine-tuned for a particular task. In this case, this was fine-tuned for sentiment analysis. And we give it, so this were how we discovered, let's do tokenization. Let's call this model, which we just named it in checkpoint. We give it a bunch of sequences, and the model produces, it tokenizes for you, does a bunch of padding and truncation. That's like, this is all boilerplate at this point. That's why I'm not even going to explain what padding or truncation is. You can just copy paste it for your task. In fact, I would even suggest a good way of learning computer science is typing it out yourself, not copy pasting, because that way your tactile sensory input is going to stay in your brains more faster. Kind of the whole idea a long time ago why we had notebooks, and still people write notes in notebooks or even iPads. But anyway, I'm digressing from the topic. So this, once we have installed transformers, we were just calling an existing model, and we gave it the sequences. I think this is repeated twice. Let's say the sequences, I love this movie, I hate this movie. It runs through all this. Okay, it already did. Yeah, so print outputs. Are you saying something? Oh, my face is not seen. Yeah, it's not particularly interesting for people to see when compared to these, I hope. Okay, so yeah, so remember the model is predicting this. It's saying here are some values, but we still don't know what the model values are. So we just tell it, hey, tell me at least what does this mean? What does this mean? And there are all these standard commands which we can use. And if the model says, oh, I think the first sentence is negative. So let's see, let's start from this 2 sentences. I love this movie, I hate this movie. I'm gonna go run after, and run after is a very interesting command. It will run everything from this one till the end, this particular cell till the end. If you're not familiar with Colab, it says, the first movie review is negative, second movie review is positive. Not exactly what we had in mind, but why is this happening? So there is this whole reason. That's exactly what I'm trying to get to, is why is all this happening? So the reason that is all happening is, how many engineering degrees do you need? All right. So these models, sure, was already trained for a general task, but we haven't fine-tuned it, or these models are not particularly, it was trained on everything under the sun. So the problem with that kind of model is, or at least in this case, we need to fine-tune it. But more importantly, there are 2 concepts here which we haven't touched upon: batching and labeling. So this is a little deeper idea of why we do batching and labeling. I'll get to that example in a second, or how we do it. But I wanted to mention a couple of things. So first thing is, remember this picture from last few classes where we are using input as the text which we were providing. It goes through a bunch of training. So like I said, this training is already done for a lot of text, not for this particular task. But then there is this gold label which we provided and ask it to learn from, which then goes back and forth millions of times. So this is the whole pipeline of neural network machine learning, technically. So why batching, right? So this is exactly the same picture which we saw earlier in a cleaner way. Labels, we find the difference between the labels and it's called loss, and we go back and forth. So the idea of batching actually comes from, terrible picture. Great. Okay, so let me show you what I'm referring to. There is this technical term called stochastic gradient descent. This is a big term. You don't even need to know. The whole idea is when we think of, so what are we trying to machine learn, right? This is exactly the picture I think I had. So when we are machine learning, we are assuming that all the data which we have right now was created by someone and has a pattern to it. There is a method to the madness. So we are hoping that there is some kind of a distribution. And the goal of the machine learning these days, or deep learning, is find the lowest part of this distribution. And when I said lowest, it actually is the lowest point in the loss, which means we start looking at the data from somewhere at top. We start with like one data point, one sentence, two sentences, and eventually we are comparing it with the gold label, and we are trying to minimize the loss, literally minimize the loss, because we are trying to make our predictions close to the actual gold label predictions. So remember, if we train it on a bunch of sentences like this movie is good, okay, that's a positive label. This movie is bad, that's a negative label. Initially, neural networks knows none of this. It just initializes a bunch of random labels predicts a bunch of random labels. We find the difference, and the difference is called loss. And this is like a basic idea that you don't even need to know how this stochastic gradient descent work. This is all wrapped around in cool functions these days. But the idea is we are trying to minimize the loss. And the reason I'm telling you about this is if we go step by step for every single data point, it's an impossible task. Let's say you have 3 million or 10 million sentences. That's going to take forever. So people came up with this whole idea that let's batch a bunch of sentences together and let's make bigger jumps. Like let's assume, take out of 1 million, we'll do a batch size of 32, which means 32 sentences. And we kind of make a hypothesis that the learning from all these 32 is going to be the same and is hopefully going to help me get down this mountain into the loss. So which is the whole idea of batching into small batches, which we did not have in the previous case. So remember, we are getting there because we did not look at batching or labeling because we did not provide the machine any gold labels. There are a few more terms you need to hear. Just be aware of this. Epochs. Epochs is simply, remember I was telling you, going through this millions of times, but how much is million, right? Or who decided the million thingy? So the whole idea is we keep going back and forth, but at some point, where do we need to stop, right? We are training a bunch of data. So the way we do it is we are training, let's say, on a bunch of movie reviews, but within the movie review, we separate it out into two different partitions. So let's say we have 1 million or 10,000 data points. Usually the separation is we take 10,000 movie reviews, we do 80, 10, 10. So 10% of it, so 10,000 is 8,000 sentences or reviews we will train on. 20% or 10% of which is 1,000 data sentences we validate on. So the whole idea is we are not trying to train the model on to predict or understand things that it has already seen, but we want it to predict on things which it has not seen. Otherwise, it's just a rule-based system. You can say, hey, I saw this movie review before, just throw out the answer positive. So there is this whole idea of when do we stop? And the answer is we keep looking at the performance in this held out data set. It's known as validation data set. So while training, we keep an eye on it, and that's called iterations. Every iterations we keep going, and one epoch is defined as going through all the 10,000 data points once. So the whole idea is once you go through these 10,000 data points, we shuffle it all up. We mix it up in such a way that, so for example, every star here is one epoch. So in every epoch, which has its own batches, comes down and we shuffle it up. Oh, this time the model learned something new. Oh, this sentence, this word is always seen with this other word. Okay, so then we shuffle it up again, run for one epoch, and it keeps going until we find this loss function to be very less. And usually you can say this training and validation loss curves. So this is how people do it. I mean, a lot of theory here, but all I'm saying is we are not trying to fit on that. Here, the red is validation and blue is train. If you look at the loss function, it's going to keep going down, down, down for the training because there is no limit to it. It can keep going till 0. But at some point, we keep an eye on the validation, and it says when this curve starts flattening out, we call it has learned something. Okay, a lot of theory. Don't need to know all of that. So which is usually like a 6 months course in itself. So let's look at data. So this is what I was saying, just some terms: epoch, iteration, batch size, etc. Now, let's go back to the original fine-tuning with batch and with label. So this is again in that, I'll share the slides, and this is already in the same page with batch and with labels. I'll go from here with batch and with labels. Open in Colab. Okay, same thing, pip install transformers. We are using this model. So usually in the previous case, if you remember, we used a model which was already fine-tuned. Now that still didn't do anything useful. Now we are going to start a model which is just very, very basic model. It's called BERT base. And we are going to start training it on with our own label. So now we are starting the training. I think we saw a little bit of this in the last class. But remember, this is only 2 sentences. That's like extremely, extremely small in the world of deep learning. We need to really have millions of sentences, or at least tens of thousands, for machine to learn something. And which is why I was going into an explanation of, hey, is this model, the model is learning from context as opposed to learning from grammar, or meaning, like last time. Anyway, the major difference I'm trying to show is these 2 sentences here. We create batches, and we also create batches of labels. So that's what we saw. And these are a couple of standard steps. So this is how you do training. So let's try this. We try pip install transformers, run again. Also, eventually, I'm hoping to get into Cyverse, where you don't have to do all this, or it's like a Docker container if you want to know what that is. Okay, so we run the same thing as before: import torch, checkpoint, start. It's training on 2 sentences, but 2 sentences is really useless, right? So right now we call all these sentences in the same batch. The machine is not going to learn anything. So let's try if it learns something. This is how you predict it. I gave it 2. I trained it on sentences. I hate Hugging Face. This course is amazing. And I tell it first sentence is 0, which I want to name it a 0 for negative. Second sentence is 1 for positive, right? So it should train the model. So it's already telling you like, hey, this is really you're not training anything enough. And I asked it to predict on these. And it said first label, I love this movie, is 0, which means negative. And I hate this movie is 1, which is positive. So that's exactly what we expected it to do, because it is really trained on 2 data points. So from here, we are going to try to train this on something more deeper. So for which I am using something known as Microsoft Research Paraphrase Corpus. So these are one of the standard models. So I'm just introducing you to some of the standard data sets, because tomorrow when you want to train on your own data sets, you can go back to how these data sets are created. So this one, for example, is a text file containing 5,800 pairs of sentences, which have been extracted from news sources on the web, along with the human annotations indicating whether they are equivalent or not. Let's look at an example. This again is found in huggingface.code.glue. And here, if you can see, the first sentence is Amrozi accused his brother, whom he called the witness, of deliberately distorting his evidence. And second sentence is referring to him only as the witness. Amrozi accused his brother of deliberately distorting his evidence. And the label is, the gold label is, yes, a human was asked this, and the human said, okay, yeah, these are equivalent to each other. So remember, the goal of machine learning is trying to make machines work like humans. or think like humans and do tasks like humans. And that's how these guys make these data sets. They come up with this whole set of training, like bunch of sentences, which are probably automatically picked from the news articles. And then they give it out to Amazon Turkers, which is just an outsourcing mechanism. So if you want to play around with a lot of data sets here, the Glue is a very good data set base. It has all types of tasks. Q usually stands for question answering, I think. The one we are looking for is this one, for example. This is the one we just now saw. And if you look at this, see, remember I was telling you about the train validation test. So validation is what we use during training. And test is something which is an extremely secretive thing, at least as far as the machine learning model is concerned. It's secret because we never want the model to have a look at the test data set. The whole idea is when we submit a result, everybody should be submitting the result on the same partition. But if the model had already seen these sentences, it can simply memorize, right? It can say, oh, every time I see the word Ambrosi, the answer is equivalent. It probably is still doing it, but that's a bigger discussion. So the whole idea is we separate out a bunch of data, the results on which people publish on, let's say, this is a famous worldwide task, Glue benchmark. So the people keep throwing models at it, and people are trying to beat the highest scores. So right now, the best score is 91.3% accuracy. That's from Microsoft. And I think this is still going. It's a very active data point. So data set that people are still trying to beat the score with new and newer architectures. But anyway, coming back to my point, the point is that, all right, what did I do? Go. Nope. All right, where are we? Yeah, so we can actually go through these data sets, and this is a data set on which we are going to train our model today. So let's go back to the same place, UA-DataLab, and All right, we're almost 30 minutes. I'll pause here for a second and take some questions on the pseudo theory which I went through, if you have any. Okay, if you are here, please open DL workshops, full training MRPC end-to-end. Give me a second, let me check one thing. Okay, perfect. Oh, didn't open, did not open. There. Let's see. So some other stuff you still need to install. So data sets. So we already saw how to install pip install transformers. Pip install data sets is nothing but the page we saw just now, which was just where was it? Okay, there's a data set page for the whole on Hugging Face for any data set you want in text world. All right. Pip install transformers torch, you should probably do only either or, you don't need both. So torch, like I said, is a wrapper or a framework which is used for machine learning, and Hugging Face sits on top of torch. So that is something we need to do. Installation, let's see. So like I said, once you're home, try to not copy paste, just try looking at it once, going back, closing the window, and trying to type it out yourself, which will give you more connection, learning, intuition, whatever you want to call that. I think this is already installed. Okay, is my network down? Or I'm probably just running way too many things. Anyway, hopefully you're trying it on your end at the same time. Hold on, guys. I'm going to try closing a bunch of this stuff I have running. Colab probably is going to block me for doing extra timelines on them. All right, that's not running. Okay, just try running it. If you can open the Colab on your end, try running it yourself. smartly close the slides for today, but there's nothing more left in the slides. All right, so let's see. Let's start running this again from top. Runtime. Where's the stop? Just refresh it. Oh yeah, what's the question? Sorry, let me check the question. Okay, so I'm assuming this is the question is, all right, slides. Okay, what is the size that is typically effective? What is the size that is typically effective size for the fine-tuning data set? Are there some thumb rules for categories of use cases? Yeah, so more the better. This is a very tricky question because neural networks, there is no thumb rule. Short answer, there is no thumb rule, right? If the more the better. So it's like an inverse ratio at this point. The bigger the model is, you really want a bigger data set, but you really cannot afford to have a bigger data set if you cannot, like if your data set is pretty small. What I've seen is anything more than 10,000 data points will give you a good result. Or even, let's say, even MRPC is 5,000 data points like we saw earlier, right? So in thousands is always better. If your data is only in hundreds, you are probably better off without a neural network. So let me point you to some of the amazing machine learning, scikit machine learning. So this is how machine learning used to be 10 years ago before neural network came in. And I think we are covering a little bit of this in our other Tuesday workshop series. If you have your data in hundreds, you are better off with this kind of standard, what we call good old AI, things like k-means, clustering, and things like that. But if you have it in thousands, you're probably in a better shape. Again, no thumb rule. Sorry. Welcome to the world of engineering and not science. I'm not denying that. Okay. I am working on something known as quantum AI, which requires only 100 data points and still runs equal accuracy, but that's not even published yet. So, but that's coming. Hopefully, people are going to get saturated with GPT not, being able to fine tune on 100 data points. Because remember, you're fighting against the learning it learned from the entire internet, and you're trying to collapse that learning into, and you're going to tell the model, hey, please kind of forget all the things you learned, but focus on these 100 data points. But it's a trial and error at this point. Okay, so let's see. Here, what we did was from data sets, we are importing load data set. I think we saw this earlier. And here, this is how you load a particular data set from Hugging Face in the bigger glue set of data. If you wanted AX, you would have replaced MRPC with AX. Okay, so you can use any model you want. I showed you a bunch of models, but the reasons I use BERT base is usually these models are very simple, and you don't have so much added complication. Like BERT base is always a good model to start with. Also, remember, this model is already pre-trained, but if you want to train something from scratch, which I don't advise, because remember, these neural networks are very data hungry, and it needs to be trained at least on millions of data points before we start doing fine tuning. But to at least play around with things, you should use BERT base. Let's say if I go Hugging Face /models, you can pick something like anything BERT base is usually good. It's a very basic model, or even if you want to save some time, DistilBERT. Anything DistilBERT is usually we saw this earlier, DistilBERT base uncased, which means it does not understand casing. So if your data set is case important, if you want something, if you have words in it, where let's say Washington, capital W, uppercase W versus lowercase w, right? If you want to learn those kind of subtle details, you might want to take a cased, which understands case. Yeah, so we saw the tokenizer last time. So this is standard stuff. We are just saying, okay, here's a tokenizer. We are wrapping it in a function. And you can literally use this straight on. Like, you don't have to understand what padding is, what collation is, and things like that. Because the goal of this lecture is not, or this workshop series is not to teach you the minute devil is in the detail kind of thing, but more to get things working. So if I can figure out why my Colab is not connecting. Wow. Change runtime type. Let's smartly use GPUs. I wouldn't have expected this to happen until later when we started the data, but apparently, yes. Okay, interesting. Okay, so remember, Colab provides you with this whole idea of you can use, GPUs and TPUs, and if you have money, you can use A100. We are probably gonna introduce you to Cybers, which has a lot of these things for free. I think this is already installed, so I'm gonna run this guy and see if that works. So, okay, so let's see what these things looks like. So yeah, this is all standard stuff. I'm trying to like remove columns, add columns, adding indexing. You can play around with your data. In this case, the data is just AB format, which is 2 sentences, right? That's not always the case. Let's see. What is this? Okay, Vinograd is also AB format. I'm trying to remember if this has, any of them has question answering. I thought, okay, so there are different kinds of labels. It's just more like, this is probably like, is one the duplicate of the other, that kind of thingy. Or let's see, if you want Hugging Face, question answering. So there are the, okay, great, models. Answering models. So you can just Google it, question answering model. So these are specifically made for question answering. And you can figure this out on how you want it to work. Okay, so it did all the tokenization. Yeah, I'm just trying to show you guys like, hey, this is how the column names on train looks like. So we remember we have train, we have validation. Did I initialize validation? Never mind. Let's stick to train. Okay, so because, oh yeah. So now this is also standard stuff, right? Okay. Remember I was telling you about batch size? So you might have a question, like you have to provide the size of a batch, which is basically how many sentences do you want to in a particular batch. And you can ask me what is an ideal batch size? Same answer as before, no right answer, no thumb rules, because this is where engineering takes over, engineering/voodoo takes over. People just play around with batch size and find out, hey, 32 works great for me. And then the reason of working great is comparing it with the accuracy on the validation set. Okay, so shuffle is true. Remember, I was saying that after every epoch, you want the data to be shuffled. That is an extremely good practice, because if you are going through the stochastic gradient descent idea, so there is this underlying theme in machine learning, which is random is good. Like humans can come up with all these weird ways for the machine to take, but ways of learning for the machine to take. But if you throw it random stuff, the machine is more good at figuring out a way out. So which is what we do. We just literally shuffle this. And in fact, if I can, there is a interesting, if I can find it, but there's an interesting XKCD cartoon on that. Eventually, I'll bring it. Anyway, coming back to our point, right? Let's see. Okay, so this kind of like does everything for you. Like we now go through each of these batches. And this was the iteration I was telling you, hey, we are going to go through the whole neural networks front back couple of times. And then this is, data loader is again a wrapper which we use on top of things. You can directly use this. In fact, if you want your own data sets, you probably have to like load it here. You can go into the load dataset function and add it. I'll get to that in a second or in the next class probably. So let's see. Yeah, so this one, we already have a model from Transformers with a model for sequence classification, because we are trying to do that classification task, which is, remember in this, the task we are doing today is MRPC 5.8 rows, and we are trying to see if one sentence is equivalent of the other or not. So you can think of equivalent problems in your world. Let's say if you have if you are trying to train a machine learning model to understand doctor notes, right? So what the way we will do is we take doctor notes and take it into individual sentences, and then we rewrite the sentence as one. The one sentence is the patient came up with a high blood pressure of 128, and I think he has angina. I'm making this up, and that's where the lack of my medical knowledge shows. And you rewrite the sentence on your own terms, which is the patient, the first sentence, right? The first sentence is patient came in with a blood pressure of 128. And second sentence, you probably can give it to ChatGPT and tell me, paraphrase this. And we're going to train it if one is equivalent of the other. There are, of course, tasks where you don't have pairs of sentences, and we'll get to that soon. Once we have this kind of a model already created, the only thing you have to do is like, let's throw it into a bunch of these. So you probably already saw this, right? Once we have the model alone can train something, but we don't want that, can predict something. We don't want that. We also use something known as optimizer. I don't want to get into that. This is all this, standard boilerplate stuff which we throw in there. For your initial class, you probably don't need all that. There is the whole idea of, learning rate, which is simply put in the picture we saw earlier. How big do you want the step to be? Do you want the step to be 1 step or 2 step, 3 step? People just, again, these are all called parameters, and people just experiment with this. We call it grid search. Okay, so this is all boilerplate. What we do is scheduler. What it does is, let's slowly start with we call it warm up. Let's start with telling the model, start with 1 step at a time, and then make it 2 steps, and then come to this value. So another thing that you can see here is, what did we do wrong? Oh, we didn't run that cell here, optimizer cell. Okay, so we ran the optimizer cell, just telling it, it's another plugin thingy, which I don't want to get into the details of it. So, okay, so this is the thing. So remember, I was telling you epochs. So epochs is basically how many times do you want to go through the data points. And at this point, like in this example, we are creating the epochs ourselves. But in truth, this is the one where I was telling you, you keep an eye on the validation data set, and eventually we will stop automatically. Like right now, for fine-tuning purpose, we're just giving it. And now the number of steps is simply number of epochs along with the number of data points in training. So which I think was 3,000 something. What is that clue data set train? Yeah, 3,003.67 rows. So is that the number that showed? Where is it? Yeah, probably less. I don't think we're giving the whole thing here. But again, you can figure out the math. And here's another thing. This is probably a little irrelevant for transformers, because, sorry, not transformers, Colab, because you are setting it here. Let's try, if I change the runtime and put it to CPU, I shouldn't do it in the middle of a run. This will just show CPU. It's just an optimization step. It's always better to use a GPU. Thumb rule. Okay, this is one of the thumb rules which works. Always use a GPU. Okay, another thing is, just if you want a cool progress bar like the one you see below to happen, just call this library called TQDM. You can just Google it too. It's a nice, good looking library. It basically says, it just shows progress bars like this, and it's already done for you here. And all you have to do is model.train. That's it. You're already calling model.train, and this function is exactly what it says. Go through each of the epoch for each of the batch. Let's collate it. And this is the exact sentence where it's learning. We take the model, make it run through the batch, and it learns something. So I'm hiding a lot of this learning part from you. But if you are just looking at getting something to work and get it off the ground, this particular page is the only code you need to know. So remember, I was telling you about the loss. The loss is basically the difference between, it's in numbers, the difference between gold and your predicted value. And gold is this label, okay, 101010. And initially the machine would just predict 0.35. And then we calculate the loss, which is simply, in its simplest form, it is 1 minus 0.33. People have come up with a lot of, crazy losses and stuff, which is kind of hidden from you at this point. This guy model.parameters already has it. So this is all, like I said, I'm not getting into details, trying to get this to run as soon as possible. loss.backward. This is exactly the backpropagation step. And that's all it's doing. So this is your fine-tuning or training. So remember, the only difference between big training, the original pre-training or the original training, is the data. It's exactly going to be the same code, but instead of your data, which is like 1,300 steps, it will be like 1,000,000 something data points. I can't even find the number anymore. Okay, this one. So now, right now, we have only like 1,377 training steps per in our entire run. But even with that, you can see this is going to take, I don't know, it's probably going to take some time. So right now we are literally fine-tuning the model. Questions? Okay, chat, sorry, thank you. Okay, silly question. To anticipate computational requirement, when you're fine-tuning with, say, 5,000 label samples in an LLM model or PaLM, what are the computational requirements? Can it be done locally with the basic local GPU or even with CPU, since the fine-tuning data set is limited, or since it reweights the model, does it need a lot of compute? Short answer, no. If you can just have a local GPU, 5,000, I'm running this on a GPU, right? We are looking at it, T4 GPU. So fine-tuning is always easily doable, which is why, people have gone towards this whole idea of fine-tuning as opposed to training. Even like 2 years ago, when I did my PhD, I was training everything from scratch. Like, we didn't have any of these big models at that time. So all the large language models we used was train, you have 10,000 data points, you literally write down, we didn't even have BERT, we wrote each of these layers ourselves and then trained on it. So clearly the accuracy was bad. So that is the answer. Fine-tuning always can be done locally. And usually a GPU should be enough. Probably never CPU. There's a deeper discussion there I can go into, but short answer, just use a GPU. Okay. Does a fine-tuning tend to happen linearly or with some sort of non-linear threshold effect as you increase the sample? I asked to understand fine-tuning sample requirements. Linear threshold effect as you increase samples. So if you increase samples, it's definitely linear, but there's a lot of non-linearity here. If you are, the non-linearity part is here. Like, remember, I was telling you this whole idea called warm-up and all. So you can read upon this, the warm-up, where's warm-up? So, okay. So there's a lot of non-linearity happening there where they exponentially start moving from, we start 1, then they go on a geometric progression, 1, 5, 15 kind of thing. But that doesn't affect you if you are only playing at the data level. It's usually linear. Instead of, if you're only increasing the data size, you're doubling it, your training time will double. But remember, that is only one of the tons of parameters. You have epochs, you have batches and things like that. I think most of them are linear. Yeah, you increase the epochs, it's going to double, double the number of epochs, double the training time. Okay, so I think this model has finished training. So now let's talk about evaluation, right? So why are we even talking about all this? Because remember, we are here. And we are here, basically, we are saying, okay, we trained on something. We also want to check how good our model is doing. And this is, remember, this is literally a toy version I coded up. But in real, actual training, this will go exactly within this for loop. And the reason for that, this for batch and eval loaders, this will go exactly within the first training. And the reason is that we constantly want to keep an eye on the validation. But this, for examples, we are just going to start literally load everything that's done for you. And this already has, all right, I don't remember where I got that from. Okay, anyway, I'll clean this up. But the whole idea is this is going to show you a metric and tell you that, okay, hey, this is, let me see, give me a second. Let me see if I can do this immediately. One time I thought I got everything right. Oh, what did I miss? Did I do that? Oh, pip install. Okay. Stuff messed up somewhere. Okay, pip install evaluate. No, so when you're running it alone, just this command alone, You don't need an exclamation point. Colab is smart enough to understand it's a Linux command. Funny enough, if you actually try running two of these together, pip install evaluate and pip install transformer, it suddenly thinks it's a Python transformer, and it suddenly says it's Python. Oh, I don't understand his commands, right? So then if anything more than one line, you have to put an exclamation mark. Just one line, you're probably fine. It's like basically command line versus Python, or Linux command line versus Python. Anyway.
Pipeline is communicating with the operating system.
The Colab pipeline is already, sitting on, these are all virtual machines sitting on top of, bunch of what I think it's probably even Ubuntu running on the background. We can, try printing it or reading on this. All right, perfect. There you go. So interesting. We got a decent accuracy. So accuracy is literally like, I ignore F1 if you don't know what that is. It's a good accuracy for, running 1,000 data points and testing on, what is that? Validation, 408 rows. And to remind you, the validation is simply, he said sentences like this. He said the food service pie business doesn't fit the company's long-term growth strategy. Okay, it's rewritten, food service does not fit our long-term growth strategy, and they're equivalent with each other. And the more important part is, this was never there in the test. So let's see if there's a nice way of looking at it. Train food service. Yeah, I might have destroyed Hugging Face by doing that search. But anyway, my point there is exactly what we saw in that lecture slide, that everything in validation is not there in train. So the goal is not, so this is the major difference between pure optimization. So the field of optimization has existed for almost 100 years now, mathematically, and people have been trying to optimize things, it's the field itself is called optimization and sits inside a mathematical department, or the course offered inside a mathematical department. But the major difference between optimization and machine learning is we are training on something and testing on something else. Optimization is literally training and testing on the same slice, but machine learning is training on something and testing on something it has not seen. So if you think about it, that's a major difference, right? So we are not asking it to predict on the sentences it has already seen. There's something deeper we are expecting it to learn, right? We are not saying Amorosi. We're not going to show Amorosi again, but we are going to say instead a new one and saying, Amorosi and probably. All right, so this is all in train. So let's go check validation and see if there's any Amorosi in validation. Say no. Thanks. Yeah. Well, that is the rule, right? We have to make sure that not just that one word, but that sentence does not exist. So yeah, we have an end-to-end full training system sitting. So yeah, which is trained on and gives you a decent accuracy. Like in the machine learning world, 0.85 is decent. Anything more than 90 is good. But hey, here is a full-fledged fine tuning in one random data set known as MRPC. You can go back and play around with anything you want. A lot of these things is self-explanatory. You can just go to data sets and, sort it by some, let's see, I don't know, image to image, right? And just see, here are the data set, facial emotion recognition. So from here, they even have like examples here. Yeah, so, okay, there you go. How to import the data sets. And usually if you scroll down, they always show you like examples. Here's a training GitHub, you already trained this and things like that. So at this point, my goal is to not teach you how to teach you how to fish, but whatever that thing is. I'm trying to teach you how to fish, not to give you a fish. So I'm just giving you one full example of end-to-end training and fine-tuning. So hope go forth and propagate, explore. I'll stop here. We have 5 more minutes and see if there's any more questions. Okay. Last question from Ajay. When fine-tuning, is there a different way of thinking about overfitting? Is overfitting based on base model, fine-tuning data, or both? Okay, so let me define what overfitting is. So the definition of overfitting is, it's a very common term people use. And this is exactly the same as the optimization example I was telling you. Overfitting is memorizing things exactly on this training data. So let me show you this train and validation curve losses. So the whole idea is, if you look at train, which is the blue line, from this point where they start diverging, this is what we call overfitting, which simply means the machine is literally memorizing things, right? It's desperately trying to reduce that loss, while validation is flattening out because it's almost telling you, yeah, I squeezed out all the juice from that data point. There's nothing more I can learn from that. So this is the kind of point of divergence in timeline, which we call, and we kind of stop the learning process after seeing this. Remember, I was telling you how many epochs and things like that. So this is overfitting. Like if you go here, now where was the question? All right, I lost the window again. All right, chat. The question was, when fine-tuning, is there a different way of thinking about overfitting? Is overfitting based on base model, fine-tuning data, or both? Will fine-tuning algorithms add layers, or do they always purely reweight? So let's go one by one. Is there a different way of thinking about overfitting? So fine-tuning also, you are doing exactly the same process, right? We are training and constantly checking on validation. Is there a different way of thinking about overfitting? So you still have to keep an eye on this graph, even during fine-tuning, which is kind of what you're subtly doing in that one sentence. Like I said here, towards the end, some of the lines which I haven't added is, check for if the validation loss is diverging. If there is that one line which people use this is called stopping criteria for machine learning. Yeah, there you go, stopping criteria. So it's basically trying to find, how do I stop, right? The people have their own implementation saying, let's keep looking at this curve, and if this is going away from the other, we call it stop. So is overfitting based on base model, fine-tuning data, or both? So the base model is huge, right? It has already learned a lot of stuff. The fine-tuning data, there is a possibility that the model might overfit, but it is much lesser of a possibility because your fine-tuning data is very less. And the model is literally trying to grab at straws and find anything that it can extract from the fine-tuned data. So usually fine-tuning is less that happens in your specified data. Will fine-tuning algorithms add layers, or do they always purely reweight? So fine-tuning algorithms, like right now, we are simply taking the exact, in this way I showed you today, we are taking exactly this model, which was already trained on something, and we are trying to tell it, learn a little bit more. Short answer, it's literally learning weights. So remember this picture? It's literally like, right initially when it came here, it would have learned, like after the whole internet being trained on the whole internet, the BERT base would have learned that, hey, this particular line had a weight of 0.004. But when we fine tune, all it's learning is, oh, it's not 0.004, it's 0.0041. So it's that little extra learning that we are hoping it will learn when we are doing fine tuning. But of course, there are all these mixes and matches, which I'm not getting into. People have fine-tuned things on different models, different architectures. But short answer, fine-tuning is simply literally the word fine-tuning. We are trying to make the weights much more sharper, hone it. Okay, any other question? We are exactly at the hour. In the class, okay, no questions in the class. Where is this thingy? All right, guys. If there are no more questions, Meg, did we already post the thingy? What is it called? The check-in thing on the chat window, right? Yeah, on the chat window, we already posted the check-in. And as usual, the slides are here on your UA-DataLab workshops, data learning workshops. I'm gonna just move all these things into that folder there, but everything we saw today is right there. Google Slides. Okay, hold on. Let me post the slide, Google Slides now itself before I forget. You share. Okay. Google Slides. Anyone with the